Everyone. Today we are doing the B63 review seminar by AMACSS, and we're going to cover the midterm from the last year. Like, it's a legit midterm. I had this midterm last winter, so it can be a very good preparation for you for the midterm for this Friday. So okay, then we should start with the first question. And so let G in F, where F is the set of all functions from n to r plus. Define OG to be the set of functions F such that. Does anybody have any answers for this? It's like the thing that you really need to know for this midterm. Like, if you don't know this, then it's not that good. So yeah. Does anybody know? Like, can anybody like raise? Yeah.
You want me to say it?
Yeah.
Okay, there exists this variable C whose constant real number. There exists n naught that's a natural number for all n or natural numbers n greater than for all n that are natural that are greater than n naught
Or equal.
Then 0 is less than equal to f of n, which is less than equal to c times g of n.
Yeah, you're right. Let me write it down. Does anybody see what I'm writing? Light? Can we turn on the light anyhow here on the blackboard?
Maybe you can use the top one for a second.
Wait, the top one. Wait. Should I like just put it down? It should be kind of better right now, I guess. Wait, can you switch on the lights again? Yeah, it should be better, but yeah, I guess like whatever. Like this definition, you just need to know. Like, just need to really memorize it for your midterm. So, okay, let's try to do the question B right now. I'll give you like maybe 3 minutes for this one. Try to do it or ask any questions in the meantime.
Actually, there's like very specific chalks. Like, you know how this is like very wide?
Yeah.
Just write harder, so it's easy to see.
Oh, okay.
And then it's like really easy to see.
Okay. Is it okay to give like 3 minutes to solve this one?
Oh yeah, for sure. And then that's great. Also, do you want to write the answer for the first one on a board just so they have it and the camera can see it?
Okay.
Yeah, see, now it's like very good.
Question 1A. No. So does anybody got the answer for this one? Can anybody tell me the answer? If no, I got the answer already, like a valid one, but maybe somebody else came up with the even better one. Yeah.
Let's say f is 1 and it's even to 0, and then g is 1.
Wait. So, okay, let f. What do we have? Like, if n is even?
Even and 1.
Yeah, this is a good one. This is an awesome one. What do we have here?
1 and 0.
1 and 0? This is not correct. I can give like the, so does anybody have any other ideas? Because like, wait, sorry, so it was like for f. What was g then?
G is
1 and 0. Then yeah, it's not correct. They are both in, like, they are both of 1, and they are like in of each other. They are both constants. I have an example that will like clarify everything right now. So basically, like, this is the correct one. N, if n is even, and n squared if n is odd. And now we flip. This is going to be our g. This is n squared. This is n. N is even. N is odd. Does anybody see why this is a good example? So basically, as n grows, f can be above c multiplied by g and below c multiplied by g for some c plus So yeah, this is the argument, because again, let's check the definition. This must always hold, like this always holds. And here, if we have this as an examples, sometimes f can be below g or above. So we fail the big O definition this way. Like it always fails as n like grows. If they're like both of the constant time, then it wouldn't work, because again, like the big O definition still holds. But yeah. So does anybody have any questions for this? If no, then I think we can go to the next one. So we got question 1c. And it's similar to question 1a. You really need to know this definition. This is very important for this course. So can anybody tell me the answer right away? Nobody? It's just the Big-Theta, that's it. Yeah.
So there exists a C1 and C2 positive fields, and there exists a not in natural such that for all n greater than or equal to n naught, C1 times G is less than or equal to F is less than or equal to C2 times G.
Yeah, you're right. Exactly. Let me probably write it like here. Question 1C. There exists plus Do you have any questions about this one? Or it's clear? It's just a definition from your notes, that's it. You just need to like kinda remember this expression. So no questions, I assume? Yeah, okay. So now let's try to do this proof. This is harder right now. I'll give you like I think 5 minutes probably for this one. Also, if you have any questions, don't hesitate, just raise your hand and ask me. Yeah.
Just a small question. Like, I have an idea of how to prove it, but similar to the assignment, when you're doing a proof like this and you have multiple C1, C2, how do you denote them? Or actually, like, how do you denote the and not?
Like a normal one.
N1, N2.
If you wish, yeah.
Like it's the same?
Yeah, there's like multiple ways to prove this one. I remember on my midterm, I just did like I used both of the omega big O, something like that. But here I just used, it's kind of simple, yeah.
I was thinking of using this, and then you choose, for the second one, you choose like C2 to equal
Yeah.
C1 and C1 to equal C2.
Yeah,
And, but like,
you can again flip, like, you can turn your Big-Theta into like, you can just manipulate the expression, this one, and get your desired result.
Probably you'll show me later.
Okay.
Like if you were to need like multiple end knots, like you write the definition multiple times, you can write this as like N1, N2.
You can even like do this using your end knot, basically. I know like what you're aiming for right now, because like I did it the same way as you are telling me on my midterm, and I got like full marks, so it's also can be valid. Right now, like actually, there's even a simpler solution. You don't even like need to even consider like different end knots and everything, but it's up to you again. Like both are valid.
Yeah. I mean, like this makes sense to me because I did it for my assignment.
Yeah.
I wrote it by hand and I typed it with LaTeX, so it's like I have it in memory.
Oh, okay, okay, okay.
All right, thank you.
No worries. So I guess we can start this question. So, does anybody have an idea how we can approach this one? Maybe somebody like got any good thoughts how we can start? If no, then like I can just go and right away solve it. But nobody? Yeah.
Just write the Big-Theta equation, and then you split that up into two parts, and then you just bring the constant down to the other side, and then you have both sides, and then you just split it again.
You're right. Good job. So yeah, basically, wait, it's question 1. Wait. Let me just wipe it like this and make it like question 1D. So, definition. Suppose F1, F2 are in the F set. This one. So, and F1 is in the Big-Theta of F2. Then we're just doing the definition, as you said again. Let the constants be B. Be multiplied by F2n. Just a normal definition right now. So everything's clear right now. Yeah, I'm just writing the definition for you to like, so later we can split it in 2 parts to get our solution. So yeah, this is our Big-Theta definition. And right now, we can note that this is an important note. So if x is in R plus, then 1 over x is also in R plus. Because again, it can be 0 and it's always positive, so this is also going to be in the same set. So we're splitting the inequalities. It's and this is this one. Now let's do this one, and 0 f1 n less than or equal to c multiplied by f2 n. So yeah, we just split it. And now we can do our manipulations with the constants, this one and this one. So this implies that 0 b 1 over b by f1 n and also 0 1 over c f1 is less than or equal to f2 n. So yeah, then we can just combine those. Does it look familiar for you? Sorry if you can't see this, it's my bad. I can write it like kind of up, or you can like kind of get closer to the blackboard and copy it, but does it look familiar? What does this one mean? This one. If you can read, sorry if like my handwriting is kind of bad, but if you can read, yeah, does it like make sense what this thing means?
Counting for big theta, like f2 in big theta f1.
Yeah, you're right. Good job. So basically, let me just write this as a final sentence, kinda. I'll write it here. So by choosing B, C, B, and not prime and not, we have, there exists B prime, there exists C prime, there exists N not in N, so that for all N in naturals, N greater than or equal to N not, we got prime multiplied by f1 by n less than or equal to f2 n c prime multiplied by f1 n. So basically, yeah, we got our big theta, but flipped. We just flip the values. And so this means that F2 is in Big-Theta of F1. Does it make sense? It's just like, yeah, A31 something type stuff, like just inequalities, and that's it. Don't forget the definition, and you're gonna do it right. So, okay, then let's go to the next question. Now, I'll give you like 3 minutes for this one, even 2. It's not hard. It's just you're gonna write, I would say, like a recursive program here, pretty much. 2 minutes should be all right. Don't forget about efficiency and stuff like that. This is not important right now. Like, even this is more important, I think, than like this question for now. So I'm just gonna, is it okay? Can I just wipe it? I think yeah. This is even more important. Stuff at the top. Just a double. Okay, so I guess we should start. So I got is AVL T. What do we need first in like pretty much every recursive program? Like one really crucial step, pretty much, yeah. Like actually in every recursive program, yeah.
Base case?
Yeah. What should be the base case here?
T is null?
Yeah. What should we return? We got like the stuff that we are supposed to return. Yeah, it's like the first one. Turn 0. And what's the second argument? True? True or false? Can anybody tell me? True? So, okay. Okay, it shouldn't be false because again, like it's null, so like it doesn't have any imbalance factor, stuff like that. So it should be like it should be true. Because it's balanced, like it doesn't have anything, so it's like balanced. And it's a valid assumption, so. And now let's just talk about our general like recursive steps. So as we are dealing with the tree, like tree consists of like right child, left child. So first we need to work with the, okay, let's work with like left child. What should we get from the left child? Like, you know, just remember your normal AVL tree functions, yeah? Yeah. You're right. We got our height of the left subtree, and we got our Boolean value saying whether it's an AVL or no. And we need to get it from the left subtree. What should we do with the right one? Is it same? Yeah, it's same. Just the normal tree stuff, like even A48 type stuff, I would say. Is AVL T right? Okay, awesome. And what's our height? What should be our height for this? Well, we dealt with like left and right. Now it's time to solve our case. What should it be? Yeah.
The max of h left and h right plus 1.
Yeah. What else do we need? We need the second value, the Boolean one. What should it equal to? Like, yeah. Sorry? It's not the menu, it's a Boolean value, so. I mean, it should be true or false, yeah. So basically, yeah, we need to have like an expression, like a Boolean expression. So what should be like, we need to we have three values inside the Boolean expression. Like, what should we check to make sure that our T is like AVL? So we need to just check the first, we need to check the absolute value of height of L minus height of R, whether it's less than or equal to 1. It's like our general like AVL tree case. But what's next? What did I forget?
Left or the right Boolean are false.
Yeah. Because you might have some imbalanced stuff like in the, like like at the depth of your left or right subtree. So you need to check for those as well. So it's going to be N the H. Wait, no, it's not H. It's B R and B L. And then we can return our final result. Does anybody have any questions here? So I assume it all makes sense. Let's go to the next question. And this is going to be super important. This you really need to remember for your midterm, for sure. So I'll give you like 2 minutes for this one. You need to like rotate stuff kind of fast, I think. You really shouldn't like spend a lot of time on rotations and everything, like insertion, deletion. So yeah, 2 minutes and I'm going to talk about this. Yeah?
What did you make for the last statement?
Return or?
Yeah, the second last one.
Wait, maybe it might be kind of messy here. So basically it's the absolute value of height of the left subtree minus height of the right subtree less than or equal to 1, like in the AVL trees, and whether the right subtree is like AVL1 and whether the left subtree is the AVL1. So this is what I'm returning in this line. Because again, like you're just checking the top and you're checking whether you had like any imbalanced stuff in like at the depth of your left and right subtrees. So this is why it looks like that. Does it make sense? Okay, awesome. Okay, I'm gonna. So just a couple more time, and we can do the B. Okay, I guess I'll start. So let me just wipe it well. This is our tree. Let's insert 21 to this. So, okay. We're going to have the 15, 5, 10. Again, 21 is greater than 15. Go right, less than 30. Go left. It's less than 25. Go left. 20. It's greater than 20. Go right. And it's 35. Is everything good here? Should I do anything?
Well, it's not balanced.
Yeah, it's not balanced. So let's check again the balance factors. So it's like 0, 0. It's 0, minus 1. Everything good here. But here we got 2 and 0. We need to rebalance stuff. And because, again, the signs are different. So we need to make like a double rotation. So first we got this go up, and then this goes up as well. So let me do the first one. 5, 30, 10, 35, 25, 21, 20, and then we do this rotation. So basically our final result should look like this. Yeah.
You know if in the midterm we have to show all our steps for a double rotation?
No, you should. You don't need to save time, but it helps you a lot because sometimes you might have like, again, here's kind of simple. You just like, you don't have any children, anything, it's just a simple one. But suppose you have like a ton of children, stuff like that, and you need to like kind of carefully work with them. So this is just an advice, like just, I'd suggest to write your steps. It will help also me like as a grader, and it will give you like part marks for sure.
Okay.
like it can save you. So the final one is gonna be 5, 30, 35, 21, 22, and wait, 25. 25. No, wait. I think I did something wrong. So 30 goes to 25. 5 here. 21 should. Wait, 21. 21 goes there. Then yeah, we got the 21 here. 25. And 22. So then we go up again. And after this, what we do is like 30 is balanced, all good. But here we also got the imbalanced thing. So, or wait, oh, I forgot the 10. Sorry. I forgot the 10, yeah. I almost got scared, like I was like, wait, we don't need to rotate, but yeah. Here was the 10, so all good. We're set up, like we can go up again, but right now everything is balanced. So yeah. And let's add 22. Let's add 22 to this. And what we're gonna do is, wait, we're adding the 22. Yeah, 22 goes, oh wait. It was 20 here. 25. And then 22 goes here, yeah. Yeah, like this. 22 goes there. This is our balanced one. 22 goes there. 30, 21, 35, 20, 25, and 22 then. Let's check. We need to perform the rotation again. And now what we need to do is just rotate here. Wait. Let me see again. Yeah, 22 went there. 22 went there. It's balanced. This is balanced. This is not balanced. So basically what we need to do is just, oh wait, it's actually, wait, sorry guys, I think I copied some stuff wrong. Let me just see again. Let me just go from the start. Again, this is why it's good to like write all your steps. So we insert 21, and then we rotate, make a double rotation. It goes there, all good. Then we insert 22. It goes like 30, 21, 25, 22, all good. 22 goes here. Then let's go up. This is balanced. This is also balanced. This is not balanced. So what we need to do is just balance. Wait. 21 need to go here. So, okay. Sorry guys, it's just a lack of space. Yeah, really sorry for this. It's just some lack of space. Kind of made me confused. So yeah, I'm going to write it down even more precisely right now. So we got 30, we got 35, we got 21, we got 20, we got 25, and we got 22. This is the imbalanced place. This is where the problems are. Yeah, sorry for such a mess. It was kind of small. Let me just write stuff here. So we need to do the double rotation again. So first 25 needs to go on top. So first we need to do the 15. 15, 5, 10, 30, 25 goes on top, 21, 20, because 25 went on top. 22 is here. So now we just need to go here. Fifteen. 5, 10, 30, no, it's 25, 5, 30, 35, 21, 20, 22. And this is balanced. Yeah. Sorry guys, I just accidentally skipped one of those, and like I was like, wait, am I doing right question or no? But yeah, everything is okay right now. Like I just accidentally missed one note. This is why you should like write all your steps. So basically here, this was after inserting 21. This one, we just performed the double rotation, and yeah, got to the right answer here and here. Then we inserted the 22. It went there. Yeah, like this one, basically. And we need to do the double rotation again. Like, yeah, we first performed it to the 25. Yeah, 25 went on top. And then, again, 25 went on top. 30, 35, 21, 20, 22. Sorry again about that. Like, does it make sense right now? Yeah, I just skipped one note and like everything just went wrong, so accidentally. But yeah, right now it should be correct. Does it make sense right now for you guys? Like, yeah. So all good. This is the final result. So yeah, let's then go to the next question. Or should we take a break or do the next question? 10-minute break?
This question is a little different. We can take a break if you want.
I mean, I think we should do the question, like question 2, like this.
I can do it in 10 minutes.
Yeah, I can do it in 10 minutes, yeah. So, okay, guys, let's do this question. This should be kind of simple. Like, it can take you like just 1 minute basically. Like just remember the differences between the weight balance trees and the AVL trees. Does anybody have an answer right away? Because like it's kind of, you already have one? Like, can you draw it maybe and like, can I see it?
My
Yeah.
masterpiece.
Yeah. I had a different one, but this also works.
Did you go to the left?
Yeah, I had like a, kinda, yeah. Like it goes to the right and to the left then.
Wow.
Yeah. I'm gonna wipe those. For example, 5, 10, 9. This isn't an AVL tree because, again, height of R, height of left is 0. It's greater than 1. So this is wrong. But don't forget the properties of the weight balance trees. So basically, for the weight balance trees, you need to check the weight of the right subtree and of the left subtree. So let's write not AVL, but weight balance tree. Because again, let's check the weight of the left side. So 0 plus 1, because the amount of nodes inside the left subtree is just 0. So you sum up and you get 1. And the weight of the right subtree is 1 plus 2 plus 3 is 3. We need to check the this inequality. So we got 1 multiplied by 3, and it's less than or equal to the weight of the tree. Does this make sense to you? Or like maybe you're confused about the weight balance trees? Because again, you just need to check the weight of the left, check the weight of the right, and check within the boundaries. So I assume it makes sense, okay? So yeah. And 3 multiplied by 3 wait, no, wait. Oh yeah, it's 3. 3 multiplied by 3 is 1 is less than or equal to 3 by 3. So yeah, we're done. This is the valid weight balance tree. So let's do the last 3 question. Yeah, last 2 basically, but it's similar. In the first question, you are doing the join with the union, with the AVL trees, like the AVL join, yeah. And in the second one, you're doing the weight balance join. So yeah, I'll give you 2 minutes for those. Wait, let me show the tree. Almost. Here are the trees. The first, try to do the AVL join, and then try to do the weight balance join. Wait. let me actually use this one. Just to make it look. Okay, so let's try to do the AVL join. So, guys, do you remember how join works, like in the AVL tree case? Like, you should remember join and split and union for your midterm. They all might appear in the midterm, so be careful with those. So yeah, right now, let's compare the heights of the trees. So the height of the left tree is 1, 2, 3. It's 3. The height is 3. And the height of the right tree is 1. So the difference is 2. And we can't just take 8 and make those children. It won't be the AVL tree. You need to do the join. Remember, like join had 3 kind of cases, and this while loop of like going down. So we're hitting that case. So basically, we're inserting R into L. So we go down, and then we go down, and we reach here, where the difference between this subtree rooted at 4 and 10 is within like 1. So we can insert our L at the here, using 8 as a root. So basically, let me show it. So we got 8 as a root. We got 4 with 4, 3, 6, 5, and 7. And for the right, and we can do this. 10 and 9. We just made our AVL tree with 8 as a root. So we finished here, and it should be the child of 2. So it should be like this. 2, 0, 1. Yeah. So right now we also need to check for the rotations, like for the balance factor. And as you can see, we have a problem here. Like the difference is between within 2. So what we do is like we need to rotate. So we got, first we have 2, 0, 1. We got 8. 4 goes here, because like it's a double rotation. This is like right heavy. This is left heavy. Like wait, no. This is left heavy, and this is right heavy. We're rotating here at the root. So yeah, first we do this rotation, like here. 4 goes on top, basically. So I got 4, 4 got 3. We got 6. No. Because this becomes the child, and this becomes the left child of 8, because it lost the 4 as a left child. So what we're getting is 6, 5, 7, and 10, and 9. And then we need to go on top again. And we got 4, 2, 0, 1. Because 2 losing its right child. 4, it needs to get one more right child, so it gets 3. And then 4 just has 8 as before. This is our result of the AVL join. What about, like, as you tried the weight balance join, like, did you notice anything like interesting? You don't need to like do all this stuff right now with the weight balance join. You just can use like your 8. You can just use 8 as your root, and that's it. Because again, this is the result. I'm just writing this way to save time, but yeah, this is going to be the result. Since again, weight of right, weight of L, weight of left is 9. It's 3. So 3 by 9 is less than or equal to 3 by 3. And 3 is less than or equal to 3 by 9. It's already like it's a valid weight balance tree. We don't need to do anything like here when we were inserting the whole tree inside, like into another tree. Here's pretty simple. Do you have any questions about those, like join, union, split, maybe? All good? Okay, yeah, so I guess that's it. Yeah. So right now I think we can take a, Jason, can we take a break? Yeah, we should take a break right now. Like, let's take like a 7-minute break. Yeah, 7-minute break until the 20.
So we'll be back at 7:20. You guys can come and ask questions during the break if you like.
Yeah, just about anything, like join, split, like union, AVL, weight balance, heap, if you want. Maybe graphs. Maybe, I don't know, maybe other course. No, joking. I'm joking, yeah. Only B63.
Okay, so for the last 2 questions on this midterm, we'll be talking about graphs. So we'll do a little bit of DFS, a little bit of BFS, and then we'll talk about heaps. Okay, so we are given this graph on the screen, and next to it you have the adjacency list representation of this graph. What we're going to do is we are going to perform BFS on this graph, and we're going to fill out this chart here. And I'll give you guys just a minute to take a look at the graph and the adjacency lists, and then we will do this part together. So as we're running BFS on this graph, we want to keep track of the distance of every node that we are visiting from A. So the distance of that node from our starting node, which is going to be A. So does anyone want to tell me which node we'll visit first?
B.
Yes. Yeah, so we'll look at the adjacency lists, the neighbors of A, and then we'll see that B is the first one there. Oh, I should write this down. And what would I write for distance? One? Yeah. And then based on the adjacency list, can someone tell me what's the next node? Because we're doing BFS, you want to visit all of A's neighbors first. So based on that, the next one of A's neighbors would be D. So we'll visit D, and then this is also one distance away from A. So we'll leave that there. Okay. And actually, maybe it'll be a little bit helpful if when we're doing BFS, we're going to make use of a queue, right? Just to tell us which one of the nodes that we're going to be visiting. So we visit A, and then let's say we have our queue here, right? And then we'll add each one of A's neighbors into the queue in the order that they appear in that adjacency list. So initially we had B and then D. And then we pop off the first elements from this queue. Remember, queues are first in, first out. So we'll take B out. We'll visit B, and then we see that is distance 1. We look at B's neighbors. We had C, E, F into the queue. Pop the first one, or I guess, yeah. And then we visit D. Take a look at D's neighbors. We'll add G into the queue. And then I guess I've kind of given you guys the solution here, but inadvertently. So I guess I'll just go through this a little bit quicker. But the next node that we would be visiting is C. Can someone tell me what I would write for the distances of 2, exactly? Okay. So there's that. And then do we need to add anything else to the queue after visiting C? No, because C has no neighbors. So this is our current state of the queue right now. And then we'll visit E, like that. And someone else tell me what's E's distance? 2. Okay. And do we need to add anything else to the queue? No. So now we have F. So we take this out of the queue, visit F, and then distance is 2. Okay. And then G, well, I mean, we can add, C to the queue as well, but in your BFS, or you can have this check now, or you can have it when you actually visit the node, but you don't want to be visiting nodes twice. So you can do either if you've already visited a node, don't add it to the queue, or when you take the node out of the queue and you've already visited it, then you just skip it. So for now, I just won't even put this into the queue because we've already seen C. And then lastly, we'll visit G. And this will also be distance 2 away from A. So does everyone understand this? Any questions? No? Cool. All right. So in hindsight, I probably should have done this at the same time as running through BFS. But now we just want to show the breadth-first tree produced by this execution of BFS. So the breadth-first and depth-first tree is just the collection of vertices that you visited and the edges that you crossed while you were running through BFS or DFS. So we'll just do this again a little quicker, and we'll do it visually, kind of. So visit A. So our tree initially has one node. And then we take the path from A to B. So this, I'm going to need more space, would be our tree so far, right? Then you take A to D. Look like that. Then we take B to C. Right? And I'll move this up after so people can see it after I'm done writing. And then we are visiting E next, and we get there from B. And then we visit F by getting there also from B. And then lastly, we will be visiting G, and we get there from D. So this, holy, this is heavy. That is going to be the BFS tree that you'll get from running BFS on that graph in this order. And the reason they give you adjacency lists over there is so that it kind of narrows down what like your answer could be. The expectation is that you go from left to right, or beginning to end of each node's adjacency list. Without the adjacency list, if you were just given the graph representation, depending on the ordering of the nodes, you have to remember that you can be visiting the vertices in different orders. So that makes sense, right? Cool. And the next thing we'll be doing is just the same thing, but we'll be doing DFS. And I'll put the graph back up on the board after I copy down the columns of this chart. Okay. So let me move this up. And I'll zoom in a little bit. Okay, so this time, as we're doing DFS through our graph, I'll also draw the resulting tree as we go through. But take a few minutes, 2 minutes, to just look at the graph and think about how you would do DFS. Remember that when we are doing DFS, we are keeping track of the discovery time of the node and also the finish time of a node. And just in case anyone forgot, the discovery time, a node's discovery time during DFS is just, well, we start at 1 and we start counting up. It's the value of this counter when we first see a node in our DFS. And then your finish time is going to be the value of the counter after you have visited all of the node's neighbors. And you increment this counter as you visit new nodes or you finish them. So you won't have any case where your discovery time is equal to another node's finish time. Okay, so we can get started on DFS. And it fills out the question fills out some starter values for you. So you have A, we're visiting A first, and it gives you the finish time. So you can use this to check if your answer is correct. You should finish on 14. So we visit A first, so you can add that to your DFS tree. And then can someone tell me which node should we visit next? Yeah. B? Yes. And can you also tell me what is the discovery and the finished, or the discovery time of B? Someone say 2? 2, exactly. So remember, we start this counter at 1, and then we increment it by 1. And then because we took edge AB to get to B, we add this edge onto our DFS tree, and then we also put our vertex B down there. Okay? Okay, so this is DFS. So what should we do next?
B's first edge, which is C.
Yeah. And then, sure, we visit C. And then what is the discovery time?
3.
3. Exactly. And then B's first edge C, B to C edge. So we add that edge, and we add this vertex onto our DFS tree. So as we're going through this traversal, we're also doing this at the same time. Okay. So we take a look at C, and then, okay. Does it have any neighbors that we can visit? No. So when this happens, we say that C is finished, and then we increment the counter again, and C's finish time is 4. Right? Okay. So can someone tell me which node we will be visiting next? E? That is correct. And what is E's discovery time?
5 and then 6.
Yes, 5. And then you're also right, we also have a finish time of 6 because E doesn't have any neighbors. So 6. And then which edge did we take to get to E? It's just one.
Okay, next is F. We take B's edge.
Oh yeah, oh I mean just like we have to add this edge to our tree. And this B to E edge is the one that we add. And then, yeah, you mentioned that we visit F next. And then what is its discovery time? 7, yeah. 7. And then we take a look at F's neighbors, but we've already seen C. So since we've already visited all of its neighbors, we increment the counter by 1, and we have this B8. Okay. And then, yeah, which vertex are we visiting next?
First close B.
Sorry?
First close B.
Yes.
Finish.
Yep. You go all the way back to B, and then you notice that, okay, I've already visited all of B's neighbors, so B is finished, and that's its finish time. And then we take a look at the vertex that we visited before, recurse up, and then it's A. And then we look at the next one of A's neighbors that we would have to visit other than B, which is D. And then its discovery time is the finish time of the previous node, plus 1. And then you guys are, oh, I forgot to add the edges. So when we visited F, we took the edge from B to do so. So we are taking, this is going to be our vertex and our edge in the DFS tree. And then we visit D, and we take this edge along with this vertex. Right? And then we look at D, and it still has a neighbor that we can visit, which is vertex G. So we do that. This discovery time is 11. And we also add this edge and this vertex to our tree. Right? When we look at G, we notice that there aren't any unvisited neighbors because we've already seen E. So this G is now finished at 12. Keep going back up. Look at D. Okay, we've already visited all of D's neighbors, which was just G. So D's finished at 13. And then you go all the way up until you reach A again. And then you see that A has no more unvisited neighbors. So A's finish time is 14. And something that's a little interesting about this question, oh, I can't move this up, sorry. But something that's a little interesting about this question is that the two trees are actually the same. And this isn't always going to happen. There's definitely, it's really easy to come up with an example of where you have different DFS and BFS trees. But in this case, they are the same. So does anyone have any questions about those traversals? So yeah, I think this course, it's a very useful skill to be able to, it is a lot of practice. So make sure you really understand BFS, DFS, rotations on AVL trees and also weight balance trees so that you can do them quickly on the midterm and the final, and then spend more time on the tougher questions, like maybe there are some proofs or stuff that you would like to spend a little bit more time thinking about. Okay. 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 So I realize I am going a little bit too fast. So this last question is the last one that we will go over today. And everyone remembers how heaps work? Let's get rid of this real quick. So in class, you learned two kind of ways to view heaps, right? Heaps, essentially, there is a tree representation of what a heap is, and that is, you can just think of that as a binary tree, or a binary tree that is two things. It has to be nearly complete, which means that at every level, you fill it from left to right. So you wouldn't have something like this in a heap, because you would have to fill this level before moving on to the next, And another thing is that depending on whether the heap you're looking at is a max heap or a min heap, for each node, you must have, it must be true that the value that you store inside this node, which I think Anya calls a priority, is, in a case of max heap, is greater than or equal to the value stored in both of its children. Right? So what I've drawn on the board is your tree representation of your heap. This representation can also be stored in an array, right? And there's a specific way that we store the values in the array. Can anyone tell me if I'm supposed to fill the first slot? No, right? So with that in mind, what would this array look like starting from the second slot for this heap?
First index, put 15, and then 14, and then 12.
Exactly. That's right. So let me add some more elements here. And then let me also just put those in. So this is 11 here. Okay, so this is your tree representation of your max heap, and then this is the array representation of the max heap. This first index is empty. You can use it to store things later, and depending on what your algorithm is, things can change. But this is just, the reason we index at 1 is so we can have some pretty cool and useful quick indexing of the arrays, of the elements in our heap. So based on this array representation of your heap, can someone tell me if you have a node stored at index k, what is the index of its left child? 2k, yes. So this, I'll write the indices actually. So 1, 2, 3, 4, 5. And then, okay, so we're looking at the root of their heap is stored at index 1. Its left child will be stored at index 2 times 1, which is just 2. And you'll see that we have at index 2 is the vertex 14. So that makes sense. And then based on that, can someone else tell me what is the index of the right child? Yes, 2k plus 1, exactly. Essentially, the way that we are storing our heap in our array, because we're filling it from left to right and then going down a level and then going from left to right again, if you have the index of one of the vertices in the heap, then the index of its right sibling is just that plus 1, right? So left child, if that's 2k, then the right child would be 2k plus 1. And you'll see that the right child of 15 is 12, and that is stored at index 3, which is 2 times 1, or well, 2 times 1 plus 1, right? So we have left child at 2k, and then right child at 2k plus 1. And those are your part A and B for this question. Cool. So based on sort of the answers from A and B, as well as a little bit of intuition, can someone tell me if you have a vertex at index, or a node at index k, what is the index of its parent?
Node of n by 2 or k by 2.
Yes. So the way you can think about this is that, okay, so let's say you have a vertex or a node at index k. If that node is the left child of some other node, then its parent is literally just, because remember, left children are stored at 2k, its parent is just this over 2, right? So that's that. And then you realize that right siblings are just the stored at the index of their left sibling plus 1. So if you have a right child, dividing this by 2 would give you somewhere in between the left index and the right, and taking the floor would make it equal to the parent. Right? So parent at floor of k by 2. Right? Okay. Oh, and these questions should seem pretty familiar. I'm sure Anya has taught you or asked you these specific questions during a lecture before. And yeah. Okay, so now the next question is going to ask you, what is the minimum number of nodes in a heap of height h, where h is the number of nodes on the longest root to leaf path? Can anyone tell me this one? Remember that a heap is nearly complete, and you want the minimum number of nodes of this heap, which has a height of h.
2 to the power of h minus 1 plus 1.
Yes, exactly. So because a heap is nearly complete, if we're saying, okay, so the heap has height h, let's say we have a heap like this, and we'll say that this is h, right? Because it's nearly complete, we want and it's the minimum number of nodes. We want to make sure to even be able to get to a height of h, we must have that all of these are full. So, but what is like this, right? This this heap, removing this last node here, is just a heap of height h minus 1 and it's completely full. And then we know then that this means that the number of nodes in this section of the heap is 2 to the h minus 1 in the exponent, and then minus 1. That is just the first. Oh. So that's just the first top part. And then we want this heap to be of height h. So we add 1 on the outside to account for this extra node. So that makes sense, right? Cool. And then based on, actually, hold on here. And then, of course, that simplifies to 2 to the h minus 1. Say we'll do min nodes height h to be 2 to the h. Well, minus 1 plus 1 equals 2 to the h minus 1. So that makes sense, right? Okay. And then likewise, we ask what is the maximum number of nodes that you can have in a heap of height h. And this is just a little bit of repeat reasoning that you can have, that you are employing here. If you have a heap of height h, and you're asking for what is the maximum number of nodes, then you just want to have, like, the heap is just completely full, right? And you'll have the number of nodes in this heap is going to be equal to 2, just 2 to the h, I believe. Oh, 2 to the h minus 1, yes. Like minus 2 to the h, all minus 1. Right? So something to remember here is that let's say you have a heap of height h, then let's say you have n nodes in that heap. So you can say let n to be equal to the size of your heap, which is just the number of nodes. Then because we have a maximum and a minimum, we can actually say that 2 to the h minus 1 is less than or equal to n, which is less than or equal to 2 to the h minus 1 on the outside. So we have upper and lower bounds for how many nodes a heap with height h can have, right? So that's something that we'll have to keep in mind for the next question. Are there any questions so far? Okay. So the next question is just a proof. And I'm sure Anya has already gone over this proof in class as well. So I'm going to ask you guys for some help for this proof. We'll make it a little interactive thing that we do. But take a look at it. And then while I erase the stuff on the chalkboard here. Okay. So, for any heap h, we want to prove that the height of h is in theta of the log of the size of h. So, remember, size of h is the number of nodes in the heap. So we'll just for easier to write, we can just let that be n. So remember, n is going to be size of the heap. And then we'll just say height of h, we'll let that equal to the to lowercase h, right? Okay, so suppose we have a heap of height h, then we know that the number of nodes in this heap, remember, must be between, I'll just write it again. Number of nodes between, in h must be between 2 to the h minus 1 and the same, but you know. So n has to be greater than or equal to 2, and then h minus 1 is in the exponent, but less than or equal to 2 to the h, all minus 1. And then we can make this a little bit easier on ourselves, and then just get rid of the minus 1 here, and then make this less than 2 to the h, right? So that makes sense. Can anyone tell me what I would do from here? So we have bounds for our n. Is there any way we can reason about h? Yeah. Sorry? Yes. So I'm going to rewrite this just so it's a little easier to see. And then you said we're going to take the log of everything, right? Yeah. So we'll take the log of this, which take the log of this first leftmost side, and this is log base 2. Yes. And just before I continue, I saw a question. Does anyone? So I saw a hand earlier. Don't have a question. Okay. Was it? Did you have a question earlier? Of a heap height h, yeah. So do you remember a heap is just really like a binary tree where you're filling up each of the nodes level by level, right? If you're asking what is the maximum number of nodes in a size of a heap of height h, you're basically asking, well, if I have a binary tree of height h, how many nodes can I fit in there, right? So that number that turns out to be 2 to the h minus 1. And I'm sure there are like a bunch of ways to prove this by induction. But off the top of my head, I can't remember any right now. But when you're asking how many nodes are in a heap of height h, it's the same as asking if I take a binary tree of height h and I fill it up, how many nodes there are. And this just turns out to be the answer. You can definitely prove this by induction, though. But I don't want to confuse anyone. So for now, just take that as a given. Okay, so we are going to take the logarithm of all three of these values here. And then because we're taking the logarithm of an exponent with the same base, these just kind of like cancel out. And you're left with, on the very left-hand side, what do I have here? H minus 1? Yep. H minus 1 less than or equal to log n, which is less than h. So looking at this inequality, can someone tell me what should be the value for h? What is h? Yes. So our friend mentioned in the back that we have h is equal to the floor of the log of n, and then you add 1 to the end. And when I learned this too, I was also a little bit confused. But if you think about it for a little bit, it starts to make sense. And I'll share my way of understanding how, or convincing myself that this is actually true. You're looking for some h that is both bigger than log n, and also subsequently, when you subtract 1 from that h, it is less than or equal to log n. So being bounded between the same value and then one of them is -1 should give you the indication that you want to use like a floor or ceiling of some kind. Initially, you might think like, oh, I want to be using ceiling here, but the values, it's a little bit easier to show, and you'll see that it's true that if I use the floor of log n, then that will be, regardless of what the value of log n is, if it's an integer or if it's not, then the floor of log n is going to be less than or equal to log n. And then to make it greater, we just add the 1. So substituting h directly over on this side, you'll see that the inequality just it's like this is definitely true, right? And then this same value, if I put it as h on the left side, the positive 1 here and the negative 1 here cancels out. And you have exactly what I mentioned earlier, how if you take the floor of any number, regardless of whether or not it's an integer or not, it will be less than or equal to the value of the number that you took, right? So this specific part, I think, just requires a little convincing to show that it's true. But once you have this line, you should be able to show that h is both, because you want to show theta of log n, right? So you should be able to show that h is in big O of log n through limits or through definition, as well as h is in omega of log n. And just as a little side thing here, we are a little bit over time, so these are not too bad. If you guys are curious, I can answer how to do these after. But once you have the constants, once you have the C's and the B's, and we'll say like n0 and n0 prime, remember that you can just, to show that it's in theta, you can take this C and this B, which is from either O or omega, and then for the n naught, to show that it's in big theta of log n, you take the maximum of these two, right? Does that make sense? Yeah, so in order to show, so these, on my midterm, I went through the definition and I showed like it's like how exactly is h in O of log n, and then omega of log n. This you can show. This can make a little exercise. I've seen people just say like h is this value of h is just in theta of log n, and then they'll get marks for it. But to be safe, you can show it through definition. So as a reminder, if you want to show that h is in big O of log n, you'll find a C and an n naught, such that for all n greater than or equal to n naught, h is less than or equal to C times log n, right? So you have to find this n naught and the C, right? So by showing this, you find these two. And then by showing it's in omega of log n, you're finding a B value and another n naught value, such that when n is greater than the second n naught, then this h value is greater than or equal to b times log n. And I'm saying once you have these four values, you need to find c and b, which you can just keep. And then for the n naught, you take the maximum of these two for big theta, right? To show that the function is in the set theta log n by definition, right? Does that make sense? So are there any questions about this? And yeah, we are a little over time. If you're curious about these specific proofs, come on up. We'll be here for 5-10 minutes, and then we'll answer them. But thank you, and good luck on your midterm.